first, for those that do not know, this is a photograph of the cosmologist / astrophysicist Reuven Opher, who passed away last year. And he was very influential in our community, as I will show you. And in fact, if you really want to know more about the life of Reuven Opher, we had a memorial symposium on January 23rd with people from, from all over the world talking about the influence of Reuven. Everything is recorded, and I really recommend you to, if you don't know Reuven Opher, to take a look at the recordings, because they're very nice historical remarks in this memorial symposium. And this is the last time we had this series of workshops that Reuven was the main organizer. So this was 2016, and you can see Reuven here. I think this was the last time he came to Brazil, if I remember correctly. And you see some of the people that we participate also in this workshop today. And in fact, Marcos Maia, who's here, is the person who really spearheaded the effort to have this workshop organized this year. So Marcos is the one that motivated people and sent emails until he found someone to organize it. So, so I just want to say that this workshop series that Reuven Opher organized was instrumental in bringing the community close to experiments. This is, in my opinion, this is one of the main outcomes of the series of workshops. And many theorists joined international collaborations, myself included, and this was one of the results of the series of workshops. And the main goals that we have is to bring the community together, the Brazilian community together, to update recent developments that we have. We're all participating in different experiments. We all have different theoretical papers also. So this is what we should do here. And then we should discuss our results. And that's why we have discussion sessions at the end of every day. So I do ask speakers of the day to stay until the end for these discussion sessions. For the old timers, used to call this the paredão sessions, because the speakers would line up in front of the audience and the audience would shoot questions. So we called it paredão. And I want to remind you that we have poster presentations as well. This was an important part of the workshop. The students will present posters, and the online format is not ideal for this, but we do have 7 posters, and they're already in the site. So there you can see the PDF of each poster and also a short video. So I do ask you to look at the posters, the PDF and the videos, and then we have tomorrow, I think, a poster session where each poster presenter can present 2 minutes of their poster. So the online format is not ideal, as you know, but that's what we can do these days. The institute is closed, most of the places are closed. And as I was saying, we can use Portuguese if everyone understands it. So it's up to the speakers if they want to speak in Portuguese or in English. The slides, I think, are in English. And yeah, that's what I have to say. So I stop sharing my screen. And I think we are on time. And the first speaker of today is Ilya Shapiro. And the title of his talk is What can quantum gravity can do for cosmology? But I think change the title.
Não, eu na verdade esqueci de trocar título.
É o mesmo seminário, só o título que muda.
Não, ao contrário, eu troquei seminário, mas não troquei título, é verdade. Então começa com erro.
Então você tem 25 minutos e depois são 5 para perguntas, tá bem?
Rogério, eu tenho que fazer full screen ou posso deixar assim?
Eu tô vendo bem, eu acho que por mim pode deixar assim.
Ok. Então, eu vou falar português, como eu entendi melhor, não? Ou teve
Você
alguém...
decide.
Ah?
Você
Não,
decide.
para mim, tanto faz, posso falar russo, português,
Russo acho melhor não.
inglês, ok. Então, eu vou dar uma apresentação sucinta de nossos trabalhos recentes e vou, no final, vou falar um pequeno pedaço de trabalho que vai aparecer amanhã no arquivo. O plano de apresentação é o seguinte: eu vou primeiro falar sobre o problema de constante cosmológica, muito rápido. Depois, sobre grupo de organização e como ela pode ser aplicada em gravitação quântica. E depois vou discutir dificuldades de obter equações de grupo de organização em gravitação quântica efetiva e como nós podemos aproveitar formalismo de Wilkowski-de Witt, que é um formalismo interessante para obter, para resolver neste caso, para ajudar neste caso, e no final vou falar sobre mostrar resultados. Então, esta não chega aos resultados que eu vou que vão aparecer no arquivo amanhã, porque lá eu acho que é parte mais interessante, mas eu decidi parar um pouco antes. Então, vamos começar com o problema de constante cosmológica. Eu já falei no workshop da Opher muitas vezes sobre o problema de constante cosmológica. Quem participou deve lembrar, talvez porque repetiu várias vezes esta história. E a ideia é a seguinte, que o problema de constante cosmológica é o problema de ajustamento fino entre duas contribuições independentes para a energia do vácuo, que pessoas falam, que nós podemos observar. Então,
Ilya, uma coisinha só. Tem uma pessoa que não entende português aqui, que é o Kim. Ele está pedindo para você falar em inglês, tudo bem?
Okay. I will shift to English, no problem. So, the cosmological constant problem is a problem of fine-tuning, and it is due to the following fact, that the observable energy of vacuum or cosmological constant is the sum of the two contributions. One is the original vacuum rho lambda. Okay, in the rest of the talk, I will not write vacuum here, it will be just rho lambda. And the second part is induced. This induced contribution comes from the spontaneous symmetry breaking, for example, in standard model, or in other theories which can exist beyond the standard model. And it turns out that both parts, this vacuum and induced, have more or less, let's speak about standard model, they are more or less of the same order of magnitude, about 10 8 power GV4, and the sum is much less. It's 10 minus 47 if you take nowadays universe. So there is about 55, 56 orders of magnitude fine-tuning. And the worst part is that we cannot explain this fine-tuning, why these two guys are adjusted with this precision. And moreover, Steven Weinberg in '87, he calculated from anthropic arguments what could be this sum such that we could exist. And he has shown that rho lambda observable should be, first of all, positive. It cannot be zero, cannot be negative. And second, in magnitude, it cannot be 100 times more than we observe. So this is a tragic situation because we really cannot explain this. From the point of view of field theory, we have this relation. So we have to change the order of these terms because rho lambda vacuum is an independent parameter, which you can find only from the measurement. All these people who say that it can be calculated in quantum field theory are completely misunderstanding the situation. It cannot be calculated, it can be only measured. But this measurement have to be implemented to this relation with too high precision. This is the cosmological constant problem. For us, it will be very important. You will see at the end of my talk. So now, So the main relation is this one. So this is observable equal to sum of the 2 points. And the sum is 10 minus 47. So we don't know why they cancel so nicely, so with such a high precision. There are many papers about this, and no solution as far as I know. And in what follows, I will not try to answer the main question. That's why they cancel and why they cancel with this precision. But I will try to see the physical consequences of this cancellation, as we did in some papers before. So now, what is randomization group? Randomization group is a kind of a useful tool to describe the effective action, the quantum corrections to effective action. And a very good example is quantum electrodynamics. In quantum electrodynamics, this is the classical action. And if we take into account the one loop contributions from fermions, from electrons and positrons to the electromagnetic part, then we have this form. In fact, this is simplification. The real form factor is not this logarithm. It's more complicated, but it behaves like this logarithm. So if you look here, you will see that for small Euclidean momenta, this box is irrelevant. Okay, and we end up with a constant logarithm. This means some small redefinition of electromagnetic charge, which is not important actually. Now, if we are in the ultraviolet, that k squared is much more than m squared, then you end up with this logarithm because mass it becomes irrelevant, and this is the so-called running coupling. This is much better than to work with the original form factor, because original form factor is the infinite derivative theory, and you need to impose the infinite amount of initial conditions and boundary conditions, things like that, which is completely impossible to do. And we don't need it, because in any fixed type of experiment, you work with the same range of energies. So going from one range of energies, let's say to electron volt physics, to MEV physics, or to ZEV physics, you just change the running coupling and you are there. So you have your theory without this form factor. It's very useful, very nice. And it is nice in electrodynamics. It would be very, very good to have something like that in quantum gravity, because in quantum gravity, form factors and all this part is much more complicated than electrodynamics. So to have this simplification of the concept is and would be, let's say, very, very useful. That's why people work a lot on some non-perturbative methods in quantum gravity. And I will show, following the 31-year-ago paper by Taylor and Veneziano, then we can do it in effective quantum gravity framework using the so-called Wilkowski-DeWitt effective action. So at that time, they did not think in terms of effective quantum gravity, but we can put this result now into this framework, and it works very nice. So let me start with the semi-classical gravity. In semi-classical gravity, the point is that the contributions to the running of rho lambda and g, the Newtonian constant, is something which we cannot calculate. The reason is that we have to take into account the contribution of massive fields, not of massless fields. Okay, and to take into account the contribution of massive fields is something we don't know how to do very well. We know some particular situations, but in some cases we can make very good calculations, but not in the case which is needed for this result. Anyway, we can use arguments like covariance in the first place. Then we can assume quadratic decoupling of the beta function for the cosmological constant. And we can use some other arguments, which I will not mention. And we arrive at these two formulas. Interesting that in original papers with Jean Sola, we have this formula for cosmological constant. And then we assumed that there is an energy exchange between vacuum and matter. And then Opher and Pelinson, the same Opher who is founder of this workshop, they wrote, Pelinson was my PhD student who just started her postdoc with Reuven, and they made very good observations that at low energy you cannot create particles. And after that, we changed the model and we had this second formula, which was also confirmed by other methods. So the question is, okay, all this is semi-classical gravity. In semi-classical gravity, we see that the result comes from basically from massive fields. Actually, nu is the parameter, which is like a sum of all masses involved. So you can see that as more masses, more effect. Then we cannot calculate this once again. We can only guess these formulas from some arguments like dimension, covariance, and things like that. But we can find the limits on nu from phenomenology, from cosmology, basically, and from astrophysics. It turns out that nu is quite restricted, but not for this model without energy exchange between vacuum and gravity. And so by the end of the day, you have some limits on nu, but this stops in this point because you have one more parameter in your gravitational theory, and you can fit data better, but it does not prove too much things. Let's go. So the question is, what happens if we switch on full quantum gravity? We go from semi-classical gravity, which when we cannot make real calculations, quantum calculations, and try quantum gravity. Then we have two big problems. First is that quantum gravity is unknown. We have no quantum gravity, which is a perfect theory. However, we can use effective framework. In effective framework, we know how to make calculations, and it looks very consistent because in quantum gravity, you have two kinds of modes: massless mode, which is gravity, and massive modes. Massive modes are typically of the Planck mass. Then we can see that these massive modes decouple long before we start any real physics, and we end up with the quantum effects of only gravitons, and in principle, it can be, the calculations can be done. And second problem is that in the effective framework, you cannot have these beta functions for rho lambda and g because of some ambiguities, which I will discuss. So in order to solve this, we need this Wilkowski and DeWitt approach to effective action in quantum gravity. And it was actually done, the calculation, by Taylor and Veneziano in 1919, but we recently checked it and we put it to the effective framework, and things changed a lot. Tomorrow there will be our preprint in archive, which shows how much things change. Okay, but so first of all, what means gauge invariant renormability of quantum gravity? This is something we need for the effective quantum gravity. So we start with any Lagrangian, covariant Lagrangian of gravity. It can be Einstein-Hilbert with cosmological constant or any other, including non-local. And using the same method, basically, as Kelly-Stella used in 77, but it can be generalized to any theory and made more compact and more complete. We did it recently with Professor Lavrov. And you can also, in our recent book on Introduction to Quantum Gravity, you can find there more pedagogical adaptation of this proof. We can prove that the contour terms in this theory are, at the first place, local. So the Weinberg theory works even for the originally non-local gravity. And second, it is covariant. It is covariant. So we have this identity, this neutral identity is satisfied, becomes word identity. It is satisfied in quantum gravity. After that, the analysis of the contour terms reduce to the power counting. So what means power counting? Power counting of corresponds to a given diagram, G, Feynman diagram, and it gives this relation. Omega is the degree of divergence, okay, which is 0 for logarithmic divergence. It can be positive for power law divergences and negative for a finite diagram. And D is the number which shows how many derivatives of the metric you have in your divergences in contour terms. So this is the main formula. It relates the number of momenta in the propagator, number of vertices, and the type of the vertex. And this theory in effective quantum gravity is non-trivial because you have two types of vertices with two derivatives, correspondingly K-nu means 2, and you can have also the 0 derivatives, which means vertices coming from the cosmological constant. Then you have also topological relation. For this theory, it's very simple to get this formula. So you see that if you have 0 cosmological constant, then the number of derivatives grow with the loop. L is the number of loops. So you have, at one loop, you have 4 derivatives. At two loop, you have 6 derivatives, etc. You never ever have cosmological constant, deep type contour term, and you never ever have Einstein-Hilbert type counterterm. But if you have your cosmological constant in the original theory, then situation changes. You have, even at one loop, you have cosmological constant, with it corresponds to two vertices with lambda. You have Einstein-Hilbert, which corresponds to one such vertex, and so on. So, and you have them in all loops. In all loops, you have this beta function to these most important two parameters, to kappa, to g, or to lambda. Very good. So, in Einstein gravity, what it means? Without cosmological constant, you have, as I said, third order, sixth order in curvature, in derivatives. Counterterms at two loop. Gurov and Sagnoti in 86 have shown that this coefficient of this counterterm is non-zero, and this proves that poor quantum gravity is non-renormalizable. People knew that with matter fields from the papers of Hoften, Weltman, Deser, and Neuhausen. We knew from the very beginning that with matter fields theory is not renormalizable. But I remember in 80s, some people thought that gravity is so important that maybe some miracle happens, and Gurov and Sagnoti have shown that there is no miracle. But for us, it is bad, because too bad, I would say, because we have effective quantum gravity. We want to work effective quantum gravity, get renormalization group equations, and we don't have them because we only have higher and higher derivative counterterms. However, if you have non-zero cosmological constant, things change. At one loop, we have Einstein-Hilbert type counterterm with lambda over Planck mass square, and then you have cosmological type counterterms of this type. You may think that this is irrelevant because observable cosmological constant is too small. It's 10 minus 47 GeV force. No, this is not true, because the cosmological constant which enters here is not the cosmological constant which we observe. This is real cosmological constant, vacuum cosmological constant, which we have in this formula. Okay, because this guy enters the gravitational action and starts to work in loops. So obviously, the situation, the cosmological constant is small in these formulas. This is true, but it is not that small as one could imagine. Okay, it's not 10 minus 60, for example, here, the coefficient for grand unification theories, it's like just something like 10 minus 6. And for standard model, it is 10 minus 20 or 30. It looks small, but you will see tomorrow in the preprint, which I will not discuss today, that it is not that small at all. Okay, it can be very big. So now how we can explore running in the effective quantum gravity? For this end, we start with your effective theory and calculate what you want, or for example, beta functions. But then you meet another problem, that the beta functions are depending on the gauge fixing and on the parameterization of quantum fields. This was discovered first time by Kalash, Tarasov, and Tutin in 78. They made this paper. And then Fradkin and Zeitlin noted that even with this gauge fixing ambiguity and parameterization ambiguity, you still have the renormalization group equation well defined for the dimensionless combination of cosmological constant and Newton constant. However, this doesn't help us because this dimensional combination is not sufficient to make some physics. So it was studied by originally in this paper by Arefyeva, Slavnov, Fadeev, then Voronov, Lavrov, Tutin, and then in quantum gravity, this mentioned paper by Fradkin, Zeitlin. We wrote it in a very explicit way with Oskar Sukhsinaev in 94. Then people checked it for gauge dependence, for parameterization dependence, and so on. Basically, the idea is that these dependencies, these ambiguities, they disappear on shell. So if at one loop, for instance, you have this form of one loop counterterms, then the difference between alpha means some arbitrary choice of gauge and parameterization parameters, and this is some fixed choice. The difference is this, where epsilon is the equations of motion. Okay. Now, if we work out these formulas, you see that in Einstein gravity you have C1, that is coefficient of the Gauss-Bonnet term, is invariant, and then this is this combination, which means basically this ratio of Fradkin and Zeitlin, which I mentioned before. So
yeah, 5 minutes. 5 minutes.
Yeah, good. How we can go out with this? So this was solved by Wilkowski and by DeWitt. and then the calculations were done by Taylor and Veneziano. The idea is that when you calculate one loop effective action, you change the simple calculus with normal variational derivatives by covariant derivatives in the space of the fields. Then it becomes invariant. If you do it properly, it becomes invariant with respect to the change of parameterization and gauge. And these are basic formulas. You can see this paper with for full details for gauge theory like quantum gravity. And we end up with this result. This result does not depend at all on parameterization and gauge fixing. And so this is the basis, solid real basis for organization group in effective quantum gravity. Next, this was done by Taylor and Veneziano, but you can make some very interesting observations. First, we can solve these equations and we get this solution with that. Second, we can note that these equations are not one loop equations. No, they are exact equations. Okay, if you go to second, third, and so on loop, they don't change. Why is that? The reason is the following. These equations have non-zero right-hand side only because there is cosmological constant. The second loop contribution is proportional to the square of lambda over Planck mass square. And in the real situations, this lambda over Planck mass square is something like 10 minus 10 at least, 10 minus 12. So these one loop beta functions at higher loops get the contributions in the form of power series, but this power series has the coefficient 10 minus 12. So you can just neglect them. Okay, effectively, it is exact. These equations are exact. And as I already mentioned, rho lambda is only vacuum counterpart. So it's not that small running. Now, for Newton constant, this running is basically irrelevant. And this solution is not very important because Newton constant is huge. Okay, it does not participate in this fine-tuning game. For cosmological constant, situation is completely different. Cosmological constant is small, yes, but it participates in the fine-tuning. And only one of the two terms is running. So the sum changes a lot. Okay, and this is the key observation, which I will not discuss today. I will go to cosmological applications. In cosmology, this means all this story that if we associate, as usually people do, mu with h, then we end up with these equations. So this is how G and rho lambda depend on Hubble parameter. And this can be a basis of the cosmological model. This is what I wanted to say about how quantum gravity can help cosmology. It is calculable for the first time, a running of these two important quantities, which you can use to construct new cosmological models. And curiously, these cosmological models are basically not subject of any ambiguity. Okay, they are not ambiguity because of we restrict to one loop. There is no ambiguity with parameterization, no ambiguity with gauge fixing, no ambiguity with anything. The only thing you have to believe is the Wilkowski-Dewitt effective action, which is, of course, a belief. Okay, but this is the price you have to pay to have two independent equations here. So let me go to conclusions because Rogerio is already looking to his watch. So we can see that if we want to construct higher derivative theory, quantum gravity, which is not related to infrared, you need higher derivative terms. But then you have many advantages and all this. However, below the Planck scale, you need to work with the effective quantum gravity. And if you assume a Wilkowski-Dewitt unique effective action, unique exactly in the sense that it does not depend on parameterization and gauge fixing, then we end up with solid predictions like this, okay, for the running G and rho lambda, and they can be used in cosmology, and curiously, it can be used even in particle physics, and put serious restrictions to the possible particle models, physics models. So, yeah, here I stop. Thank you very much, Rogerio, for inviting me to give this talk. That's all.
Thank you. This is amazing. So I'm looking forward to our paper tomorrow and for the discussions this afternoon. So we have time for a couple questions for Ilya. You can raise your hand and I can, or we our mic. I have a question to start with. So Ilya, I have several questions. Let's start with one. So you have an equation for rho lambda as a function of the Hubble function, right?
Your sound is fluctuating, Rosario. Can you repeat again slowly?
Yes. So you have an equation for rho lambda as a function of age, right? Yes. But age is a function of rho lambda as well by Friedman's equation.
Exactly.
So you have a coupled. So that'll be interesting to see the solution because one influences the other.
Yeah, this is you need to work out these equations, the full set of equations, and construct the cosmological model. You need to have the full set of equations. These equations include Friedman equation, okay? These two equations and the conservation equation for energy, okay? And in this case, there are some possible difficulties. I can foresee some possible difficulties in constructing the cosmological model, but they can be solved, and we basically know how to do it. Okay.
But in your approach, the cosmological constant is not a constant, right? It depends on.
And, Newton constant is.
And map this to this usual parametrization of the variation of dark energy. You're aware of this, W0, WA parametrization of the equation of state. And that'd be very interesting because that's what.
Yeah. Some people did this. I never did it myself, but I can give you references when people did this with the semi-classical equations.
Okay, very good.
So this is one of the possibility. One possibility is just to trying to solve it. Okay, Friedman equations. With logarithm, it can be difficult. Now, another second possibility is to, as you said, map it to the equation of state. Okay, so you replace cosmological constant and Einstein term for some, let's say, matter action, which gives you this equation of state, which corresponds to this correction. This can be done. And the third possibility is what Opher and Pelinson used in their paper, is to make a mapping to the scalar theory. And yeah, this is also possible. And in principle, to make mapping to the scalar theory, I like it most. But you need to first typically to solve, as Julio explained me some time ago, you need first solve the equation for A of t, for the conformal factor, which with logarithm may be non-trivial, but also not impossible. Okay, remember that logarithm is slow function, so in principle you can just expand it to first to second order and work in this way in the worst case scenario.
Yeah, you're as you know, we can always do it numerically. You don't have to.
Yeah, but logarithm. No, okay. And logarithm also is important to remember that logarithm has degeneracy when h goes to 0. But in the real world, h never goes to 0 because there is infrared cutoff because of the global cosmological constant.
Right.
Okay.
So we can discuss more in the discussion session. This is really, really interesting. Thank you, Ilya. So now we go to the second speaker, so Valerio Marra, directly from Trieste. So Ilya, can you stop sharing, please? And Valerio will start sharing.
Hi, Rogelio.
Hey, Valerio.
Everybody. Let me share everything here. You can see everything, right?
Yep. Please go ahead.
Okay, let me minimize your faces. It's nice to see some faces, but not too many, so now I cannot see my slides, right? All right. Yeah, because it's difficult to talk without seeing anybody, right? These virtual talks are not easy for the speaker. All right, so thanks again for inviting me. So I'll talk about the status of the Copernican principle in light of the latest cosmological data. I'll take some detours during the talk. I hope you find them useful. So, okay, so this is just one slide to summarize a standard model. Is a pie chart with a lot of dark stuff. This dark stuff is 95% dark matter and dark energy, and 5% is what we know from the standard model. And this is an old slide from Rocky Cole, and well, he used to joke on this because these slides really tells you how insignificant are chemists, how is chemistry as compared to physics. All right, so going to the motivation for inhomogeneous cosmology. So first, what is inhomogeneous cosmology? So the study of cosmological observations without assuming a large-scale homogeneity and isotropy. So the first motivation could be just to, we have 95% dark universe, you better test your assumptions to see if they are solid. Second is also interesting, independently of the dark energy and dark matter, to study the universe without assuming large-scale homogeneity and isotropy. That is, without assuming any Friedman-Lemaitre-Robertson-Walker metric. If you want, the grand goal would be to reconstruct the metric, at least the local metric, from observations directly. Of course, you pay the price of a reduced statistical significance on many parameters, because you with less assumptions, you need to constraints widened. But it's anyway an interesting endeavor. And lately, a big motivation has been that actually there could be a large-scale inhomogeneities and isotropies that cannot be explained by the standard paradigm. And this has been suggested, for example, from the tension on H0 and from various anisotropy claims. Famous ones are the one from the quasar distributions and from the radio dipole, for example. You know that if you have a large scale dipole that does not coincide with the same CMB dipole, FRW is in big trouble, right? Okay, so the model that I am considering here is the simplest, I call it the spherical cow, because the simplest extension to the standard paradigm. So, well, first, CMB is isotropic to a very good degree. There are some hemispherical anisotropies and tensions, but they're very small signals. So to a very good degree, the universe does look isotropic. So it's kind of justifiable to take to consider an isotropic model around the observer. Anyway, this is just the first step. Of course, you would like then to generalize this kind of models with some more flexible way to parameterize the large-scale inhomogeneities. So what is the lambda LTB model? It's just the standard lambda CDM model endowed with a spherical over or under density around observer. And this is actually is not limited to this scope, because you can actually study anisotropy claims just by placing the observer off center. But this is I won't talk anymore any longer on this. So just to summarize the slide for the metric. So this is you can see my cursor, right? So this is the LTB metric. It's written in a way so as to hide the dirt, the dust under the carpet as much as possible, because this looks like FRW. It's just that you have some extra R dependence here and there. For example, the scale factor depends on R, the amount of matter depends on R, as well as the curvature, etc. The relevant, so the key point here is that once you have spatial gradients, so that you have a profile that's not homogeneous, not always, basically, I think, I don't know, there's no theorem, but the solutions I know, you have different expansion rates along the line of sight and across it. So this is a general feature. And this we call it background shear. And can be tested very easily with the observations, for example. So this is the metric, and you have two free functions, essentially, which are the curvature. So by perturbing the curvature, you basically add an additional growing mode to your universe. And then you have the bend time that tells you when the universe, when the scale factor was 0. And by perturbing this, you have a decay mode. So we don't want decay mode, so we just have a model that is parameterized by a given curvature profile. Okay, in this case would be just the size of the perturbation and the depth of the perturbation. So this is just to give a plot. So this delta naught is the contrast at the center, and CB is the redshift of the boundary. And these are the two inhomogeneous parameters that we add on top of all the other lambda CDM parameters. So here is an example of an underdensity. And the blue curve is the local density. So you see that you have, in this case, a central underdensity, which is compensated by a ring, a kind of a shell, a compensating shell. And vice versa if you have a central overdensity. On the right, you can see on the light cone the expansion rates, both of them, the transverse and longitudinal. You see that they are different when you have spatial gradients. As soon as you don't have spatial gradients, they become the same. And in this case, you see that the local underdensity boosts the local Hubble rate. So it seems like you could fix the tension, right? This will actually be one of the main topics of this talk. All right, so then to understand how to judge a given inhomogeneity, as we are giving arbitrary inhomogeneities, we need to describe what is a standard inhomogeneity. And we do this via what we call the Copernican prior, which would be like the statistical counterpart of the Copernican principle. So it is this one on the top. So basically, it's just a Gaussian distribution where this delta would be the contrast of your homogeneity of a given size, ZB, is written in this funny form because it has some radial gauge freedom. And on the denominator, you have the standard root mean square fluctuation given by your power spectrum. And then you convolve this guy with the CMB likelihood so as to account for uncertainties in the parameters. So basically within standard model, you're allowed to generate perturbation via this distribution. The data that we use are the latest CMB spectrum, Thomson supernovae, both the full set and only the low Z sample. Low Z sample is the one that is used to determine H0. Cosmic chronometers, BO, contour distortion, Dodge effect. These last two are very useful to constrain very large scale inhomogeneities. And finally, the local calibration by shoes, which is basically the constraint on H0. Now I'll take a little detour regarding this. So how does shoes determine H0? Or also CCHP, which would be the Carnegie group that led by Wendy Friedman. So it's a two-step project. First, you put together calibrators to calibrate supernovas, the supernova magnitudes. And in case of shoes are basically Cepheids, and in case of Carnegie group is the tip of the red giant branch. Then second step, you apply this calibration to Hubble flow supernovae and get your constraint on H0. Okay. So what we've been arguing is that when you do your cosmological inference, it's better to skip step 2 and just adopt step 1. Why? So because first you could double count supernovae. Second, most importantly, if you're constraining your interactive dark energy, dark matter model, you don't need to use cosmography, right? You already have an H of Z, so you better use that instead of a cosmography, which is actually fixed to the standard model value of Q0 minus 0.55. And third, also, you add some statistical information on the fact that supernovae do not have arbitrary brightness. Actually, this is constrained by local calibration. And including this information, you can exclude weird models like this hockey stick dark energy. So we are keeping updated this prior on the absolute magnitude, which each data set has its own because it depends on the calibration. And you can use it. There is already the module in MontePython 3.5, was written by my student David. So two simple applications. The first is that you can do different analysis that shoes did not do. For example, again, you can use your F of R model, or you can simply do a cosmography marginalizing over Q0, right? So the three parameters here are H0 you want to determine, MB, which is calibrated, And Q naught, that you could fix it, you can marginally derive it, you can change completely HOZ, use whatever you want. So the result is that if you free Q naught, your constraints change a little bit, and to our surprise, actually H naught increases its value. So it's higher than before. The tension does not significantly change because also the error bar a little bit increases. Okay. Another use of this MB prior is to look at the H naught tension via so-called the MB tension. So to quickly say it, you can do the distance ladder going from today to the same B, or vice versa from the same B to today. So if you do the inverse distance ladder, you start from the same B, you have your standard ruler, which is the standard horizon. Then you observe it again thanks to BAO. Then you can do, for example, you can use many techniques. So a technique that the VNI proposed is to do a calibration that is based just on the distance duality relation without doing any cosmography, any modeling. And once you do that, you propagate from BAO to supernovae, then you get a calibration from CMB directly. And using this, you can have an equivalent crisis that is not on H naught, but rather on the calibration of supernovae. And then with Leandros and collaborators, we argue that this could be kind of some weird transition on effective Newton constants, but I won't talk about this. However, this is yesterday's story, right? So I think everybody knows that last week there was this big seminar by Dan, Adam, etc. So there is now Quantum Plus, 1700 supernovae, many more at low redshift. They did a fantastic job on now they fit everything at the same time with a big covariance matrix. So this is the supernova, right? This is all set. It's a huge covariance matrix all done at once, and now it's a phi sigma tension in log space, however, not directly in H naught space. And so this was the big event because finally the phi sigma threshold was reached. So big excitement. And now they listen to the community, to people asking for this. So now the local prior is given directly by them. We don't have to do like the reconstruction that we did. And they will put a cosmosis likelihood with all the calibration of the host supernovas and anchors that you can. So you basically do the calibration and cosmological analysis at the same time without having to do that cosmography that is useless if you have your model. And so this is a very good news. So soon there will be cosmosis, but anyway, still, if you cannot wait, or if you don't use cosmosis, use Monty Python, you can still use our simplified method, and which you already updated with the new constraints. Okay, so this was just a little detour. So, can a local void solve the H naught crisis? I showed you that plot. That you see that clearly, if you have a local void, you have an open universe, faster expansion here than there. So the answer is, let's see. First, if you stick to lambda CDM, you are bound to the structure that are allowed by lambda CDM. So this is called cosmic variance on H naught. So this on the left is amount of fluctuation of H naught as a function of the scale. So if you convert this with the supernova distribution at TUs, blah, 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 you have basically half a kilometer per second per megaparsec. And you need 6 to fix the tension. So there is no way that a standard lambda CDM perturbation can fix the tension, right? So this is kind of this was an open debate, and now it's kind of I think is accepted. However, what about an arbitrary? So let's forget about lambda CDM. Let's say that you have a funny initial power spectrum from a weird inflation. So if with an arbitrary inhomogeneity, yes, you can. Right? So if you consider low redshift supernovae, this is the range that's used by RIS, and the data, so the green contours are what the Copernican prior lambda CDM tells you. So this is what is allowed. But data tells you do not have this prejudice. Data tells you that a big underdensity can give you an H naught, which is close enough to the tension. So we would say, okay, let's drop lambda CDM, let's drop, then we fix the tension, solve it. Not so easy. As soon as you add all supernovae, just supernovae, you don't need to add any kinetics, Nedeljkovic fancy stuff. You just add all the supernovae, and these red underdensity contours, they go away, and you go back basically to the standard model. And there is it's not possible anyway to solve the H0 crisis with the local void. Okay, so in taking this now, going back to I hijacked a little bit the title of the seminar, so going back to constraining spherical homogeneity with observations. So this first plot was actually just to tell you about the possibilities of observing or fixing the H0 crisis, but it's not really relevant to constraining homogeneity because you would use only the Loreschi supernovae. So if you have all your supernovae, then if you add BO and H of Z data, you add Y distortion. So Y distortion basically is due to the fact that if you have structures on your light cone that are moving away from you or towards you, anyway, if they have a significant relative velocity, they would reflect their own CMB, what they would see, that is a different temperature, and then would cause this Y distortion. Nedeljkovic is due to the fact that you have these hot electrons that are moving fast with respect to the CMB, and this would add an extra signal. And again, we have limits from soft pole telescope on this. And then so you see that by adding more and more observations, maybe it's not so clear because with all the supernovae are doing already a very good job. But yes, if you add more observations, you reduce more and more the available parameter space, and you really go near what is expected by lambda CDM. And yeah, this actually was supposed to tell this before, but so this again is the same things, but on H0 was showing just that the tension goes away. And this is basically the best fit model. So it shows that the best fit model is indeed a local underdensity, but not deep enough in order so as to explain the tension. Okay, so going back to the constraints. So here on the left, I'm showing a plot which tells you how much more structure can you have in a given scale as compared to the standard model, the Copernican principle. So when there is a hole, means that you cannot have any more structure because you constrained beyond the cosmic variance limit. And the two colors, the pink colors is when you include all observations. So you see that indeed there is a gain from all supernovae plus all supernovae and all the other observable, especially at a larger scales. However, one has to keep a caveat in mind here that this is a very specific modeling. So once you reach a precision, a constraining power so high, of course, you need to start worrying about systematics. And in this case, systematics are the assumption that we made on the profile. So it's a profile which is spherically symmetric, which is monotonic, and which has a fixed shape. So it can stretch, but cannot change shape. Okay. Why we did that? So we did that because we wanted to probe in a democratic way both underdensities and overdensities. And in LTB, there is a little issue that it's in a synchronous gauge. So if you do not choose your profile appropriately, you can have shell crossing. So basically, you lose portions of the parameter space in an artificial way. So you would find that some parameter space is less probable, but not because it is just because it's an artifact of the model. So for this reason, we chose a profile that almost never gives shell crossing. And in this way, we were able to probe both under densities, over densities in an equal way. But of course, in the future, I think one should, I think we reached the limit for the LTV modeling from this point of view, and one should consider perhaps a more flexible approach.
Valerio, 5 minutes.
Thank you.
That's it.
Yeah. Went too fast.
Perfect. So thank you very much, Valerio, for this nice talk and bringing in these new results of Rees and Dennis Koenig and others. That's really incredible what they have done. And let me ask another thing before. So you probably won't be able to join the discussion session because you're in Trieste and maybe too late for you. So
yeah, maybe.
Yeah, maybe we can, since we have a break after this of half an hour, we can extend, if you don't mind. If there are more questions, you can stay over, and then you don't have to come late in the evening for you for the discussions. Would that be okay?
Sure. Yeah, sure.
Okay, so let's open the floor for questions for Valerio. You can raise your hand in Zoom, or maybe just open your mic and ask a question. Just go ahead.
So Valerio, I can ask a question. Sorry.
Yeah, go Miguel and then Marcelo.
So you're saying that you're in the edge of LTB already. You cannot use it anymore, and it's more sophisticated model. But if you just use LTB, but you're not in the center of LTB, did you try a bit? Does it help a bit? And
so you want to do that because for this dipole, essentially for quasars in radio dipole anisotropies.
Exactly.
And supernovas anisotropies as well. So I could have a backup slide. I forgot to put it. So basically, you have all these dipole hemispherical isotropies that kind of point through the same direction, just they have a different amplitude. So it'd be interesting to do this. And well, this is a human power constraint. So I mean, what is missing is just you need to write a module so all this code is publicly available. It's called Montevoid. And you can, well, I don't know if Davi already put it completely, but you can ask him. It is unofficially and will be officially publicly available. So you can do your own analysis. So what he should write now is it's a module to take into account of center observer. And this is not trivial because when you're at the center, you don't have to do any ray tracing, just solve one dimensional differential equation and you have your light cone. When it's off center, it's a little bit more. That's been done, so it's totally doable. But you need to do it in a robust way that you can put inside MontePython around your MCMC.
But besides this dipole, radio dipole, and this, all the dipoles that you could, of course, if you want off center, will be introduced. Do you expect any change in the H0 tensor itself because of this? I mean, is there any isotropic data that could be, try to fit because it's no longer possible?
Well, you will obtain from your analysis the position observer without respect to the center. So this will, this is significantly away from the center, it will be very interesting because you will know that the data themselves, they prefer this kind of anisotropies in a consistent way because you put all the data at the same time, you fit all the same time. Regarding the H0, well, there is the thing that supernovae. So if you go to if we go back to the slide of the Pantheon Plus, you see, I mean, we need to wait for LSST in order to have a uniform distribution of supernovae in the sky, because this kind of is difficult to read this, because these are survey names, it's not rashes. But basically, I think that all the ones that are uniform distributed are low rashes. And the high rashes are kind of they're like pencil beams surveys. So that would be really interesting. So because supernovae can, of course, be put for strong constraints, and especially because they are so directly related to the H0 tension. So if you would find anisotropies significant in the supernova distributions, this could impact H0 tension. But I mean, I would say that is difficult, but I think one should totally do it, and the off-center LTB is the easiest way to do it. But then really, I think one has to LTD is nice because it's a generalistic solution. So it's beautiful, right? Just for that. But what is given that the contrast that you see, there is no need for an exact solution when you constrain stuff to this level. Basically, linear, totally linear constraints. You can just work on Newtonian gauge, your potential, and you have all the profile that you want, and you can model with nodes of spline, etc., without shear cross, without. So one should do this kind of analysis now, I think.
Thanks.
Okay, Valerio. Marcelo, please.
Rogério, do I have the time for 2 questions? Just one?
Yes, yes, you have time for 2 questions.
Okay. My first question is about isotropy. It's not clear to me in which extent you assume an isotropy has a role in your analysis, assuming that there are some not non-consensual indication of isotropy in the data, CMB, for instance. And so my question is, what's the role of isotropy? I'll also ask this question because people forget that in mathematics, we've got Friedmann-Hauswalker models that are homogeneous and isotropic. But if you have homogeneous world, but which is not isotropic, you have to use certain geometries, and there are 8, not only Friedmann-Hauswalker, to model the universe. So isotropy, local isotropy, to be more precise, is crucial. And isotropy leads to the 3 Friedmann, together with homogeneity, it's local, leads to the 3 Friedmann-Hauswalker universe. It's isotropy, local isotropy is broken. You have to consider a wide class of geometry that was discussed by Thurston.
Yeah, so no, I totally agree that one should include isotropy. So this is I told you, this is the spherical cow. So this is the first extension beyond LCDM, but then you have to, especially because the observers that one can study, so BAO, HOZ, Y distortion, all these observers, they probe a different redshift range. So in principle, you can have different isotropy at different redshift range. And again, in isotropy, it doesn't have to follow lambda CDM paradigm, it can be of arbitrary size, you just have to constrain it. And quasars and radio and CND and isotropy, all this. So the only thing that this analysis is not, I mean, it is relevant to some point, is that an isotropy, if it is violated, is not violated by 50% effect. It's anyway, we're talking about percent effects. Also,
so you permit an isotropy, is that right?
Sorry?
In your analysis, you allow an isotropy.
No, not yet. So the next step would be to place the observer off center. So you introduce how big an isotropy you want, and then you constrain that too. But that's technically much more difficult. But again, if we can, we'll do it. And but I agree that the next step is to include an isotropy. One has to. Does it make sense to, I think, to improve on an isotropic modeling of the universe? One has to include anisotropies for sure. That will be my next goal. Yeah.
Okay. Marcelo, you have another question?
Okay. My other question relates to the concept of homogeneity and what you, at the end of the day, are making when you do this sort of analysis. Just to remind you that at one point, we've got local concept of homogeneity, but we also have global and topological concept of homogeneity. You are not dealing with the global I understand that. But my point is that even locally, you've got at least 3 approach to homogeneity, for instance, which is if you consider only mathematics. If you consider only mathematics, you only need to use group of symmetries and find out the action of the group on hypersurface and decide whether or not the action is transitive, simply transitive, etc. This is mathematics. On the other side, you've got another ingredient, that's the data. And in the data, you basically, to speak about homogeneity, you have to choose a scale. So in one hand, you have a model, a mathematical way of approach the data, and the other hand, you have the data. So at the end of the day, what you are doing with this sort of work, it's admitting that you are dealing with a model that is mathematically homogeneous in the group sense, and assuming the data that we can see, we can measure, we can detect, and trying to make a consistent pictures of this. A consistent pictures require some constraints. That's the way I look, which can be explored, of course, but that's the way I look these sort of work that you are involved with. You are checking consistency between, in other words, can I model the universe with a Friedman-Howells-Walk homogeneous model with the data in which scale, and what are the consequences? Is that right, my way of seeing your line of research?
So then, see, yes, in homogeneous cosmology can be an unsolvable problem if you take it too wildly. So you got two approaches usually are taken. So the first is perhaps closer to what you're saying. So these are called null tests. So you just assume that, let's see that, let's suppose that Friedman Lemaitreux's work is correct, and let's see if you can falsify it. Some consistency relations. You try to falsify it to see the consistency of this assumption with observations. So that's one way, but it's powerful, of course, because it's a consistency test. You're not adding parameters, so you don't increase your parameter space, and so you don't decrease your constraining power. But it's not necessarily if you find something will tell you it's not doesn't necessarily lead to understanding why and where and how this violation happens. Yeah. So the other avenue is so you always have to start, I think, when the cosmological data are too vast. I think you need to start from some smooth deviations from the standard paradigm. So this is what people have been doing with all so F of R deviates from standard from R theory and coupled arc energy. So
yeah, sure.
So this is the same thing. So you perturb large-scale homogeneity and isotropy with some extra freedom, and then you constrain it. And again, one always has to keep in mind the caveat that all these data were analyzed and tested, all the pipelines, all the mocks, assuming the lambda CDM model. So even more justified to take as most deformations. So yeah, so this is the approach. So if one would find that a very non say that the universe that is far from FRW was preferred by data, then you should be careful to see if all the data were analyzed correctly because you're switching the fiducial by far. In our case, as we found back the FRW, basically the FRW limit, we see that there are large structures which allowed but a very small contrast. We're kind of confident that the data analysis is not too badly done, right? Of course, when there's nothing to do when you include data that results that were analyzed with different fiducials, you have to keep in mind that there could be a bias, but that shouldn't be so big given the final results. Yeah, I don't know if I answered your your question, but basically.
Do you assume flat model in this analysis?
So we did two analyses. One with the background. So these models are matched at a finite radius to FRW here, and so you see here on the left that at RB they match exactly the FRWs, not at an infinite radius, at finite radius. So we did a run with the background that is a zero curvature, and also run with free curvature, and the result wouldn't change much. And, yeah, the constraints are not not much different. Basically, the CMB so strongly, and also because, well, from the geodesic point of view, once you have a compensated inhomogeneity, you kind of cancel partly the effect on the CMB. So CMB keeps its power and constrain the curvature close to zero.
Good, thank you.
Thank you, Valerio. Okay, other questions? So I have a question that maybe you already addressed, but so you found out that the best model that fits the that can solve the is an underdensity. So my question is, if that also affects the S8 tension, how does it affect the S8 tension?
So I haven't thought about that actually. So you can see it from here. So it's a very small, well, just say half a gigaparsec, but it depends how you count it. So this wouldn't change any weak lensing data, any number counts. So this wouldn't, I don't think it would change. But again, this kind of analysis was not, this modeling was not a design having in mind and trying to solve, for example, the S8 tension. So, but yeah. Okay. So basically, if you want to have less structure lately, so an open model should do, right? So perhaps a very large. So you see that it's a good question actually. You see that you can have large scale inhomogeneities that are allowed. So if you have a little, say minus 0.05, very large scale under density, probably that will pass the tests because, well, the contours end here because with the MCMC you cannot go in. It's difficult to go into sampled regions, but probably you can have a very large scale under density with a very small negative contrast. That would give you a little different. I don't know if there would be any impact on S8 tension. Good question.
Thank you, Valerio. So any other questions for Valerio? Remember that Valerio is in Trieste, so he will not be able to join the discussion sessions for him. So this is our last opportunity to ask questions to Valerio. Okay, I don't see any questions. So let's thank Valerio and Ilya for their talks.
Thank you.
And so we reconvene at 11:30. Okay. So the idea is to have a light meeting. So we reconvene at 11:30.
Bye bye.
Bye-bye.